Great. Okay, welcome back, everybody. So our next talk now is going to be from Matthew Jenssen from King's College London, and he's going to talk to us about the hard sphere models, sphere packings, and algorithms.
Okay, thank you very much for having me at this wonderful workshop. What I'm going to talk about today is a sort of circle of problems in maths, physics, and computer science. And one of the things I like so much about this topic is all the different ways you can look at it. And then at this workshop, I've discovered so many new ways that I hadn't thought about before. So it's been really wonderful seeing all these beautiful talks. So I'm going to start off with one of my favorite problems, and given the title of this workshop, I suspect you might like this problem as well. Sphere packing problem. Okay. Oh, no, it doesn't like my keyboard either. Oh dear. Let me just unplug this clicker. Oops. We're up to a bad start.
Not going to work.
Need that with the display.
Oh, it's coming.
Yeah. Oh, great. Okay. Sphere packing. So I have to stand here because I don't have my clicker. That's fine. So the basic question is, how densely can you pack identical spheres in Euclidean space? So here we have this picture of a packing of cannonballs in the face-centered cubic arrangement. And I'll denote this packing density, the maximum sphere packing density, by 5D. So D is for the dimension of space that I'm living in. Largest fraction of space that I can cover by non-overlapping identical hard spheres. This is a very basic question, and surprisingly, well, not surprisingly to this audience, but this idea is only known in a handful of dimensions, namely 1, 2, 3, 8, and 24. So this sort of casual line here is hiding a sequence of spectacular breakthroughs, starting with Thomas Hale's amazing resolution of the Kepler conjecture in dimension 3, and Wierzowska's breakthrough work in dimension 8 and 24. But what I want to talk about today is the same problem in large dimensions, so getting away from low dimensional space. So how does the packing fraction behave as D tends to infinity in a very high dimensional space? What can we say about the sphere packing density? So let me give you a very simple lower bound. Perhaps some of you have seen this already, of 2 to the minus D. I'm going to do a proof for you using my hands. I'm just going to throw spheres into a box, keep throwing spheres until I can't squeeze any more spheres in, and I'll say I'm saturated at that point. Okay? So now imagine I have the saturated packing, and I'm going to double the radius of each sphere without moving the spheres. So they're fixed. So double the radius. These double radius spheres can now overlap. And indeed, they actually have to cover the entire space. Why is that? Well, if I have a point that's uncovered, that means it's twice the radius away from any other sphere. That means I could put another sphere there, contradicting the fact that I was saturated. So now I have, suppose my initial sphere is volume 1. I have a collection of spheres of volume 2 to the D covering space, and my initial density must have been at least 2 to the minus D. So any saturated packing actually has density at least 2 to the minus D. So it's a very simple argument, just a greedy lower bound. This is basically the state of the art. So
is that close to the answers for 8 or 24 dimensions?
Not at all, no. So much lower than if I put an 8 instead of a D there, this would be much lower than the D8 lattice density. Okay, in 1905, so there's been 100 years of effort and more on this problem. In 1905, Minkowski gave a small constant improvement to this lower bound.
Actually, just a question since we're is lunch next, or do you have infinite time?
I don't think I have infinite time.
Large.
But go, yeah.
Let's do it.
Questions are welcome, yeah.
But that same greedy algorithm works with some constants out front for sort of anything that's kind of.
Ellipsoidal?
Yeah, I mean, is it right?
Yeah, yeah.
So
any centrally symmetric convex body this works, yeah. It's not just spheres.
Yeah. Okay.
Exactly.
I wanted to make sure.
Absolutely.
Everybody.
Yeah. So the first breakthrough came in 1947. So Minkowski got a constant factor improvement, and then Rogers managed to get this extra D out front. So linear improvement to this 2 to the minus D bound. And then the race was on to improve this 0.73. So there's a sequence of results improving the constant by Davenport, Rogers, Ball, and Vance over the 20th century, culminating in the world record by Venkatesh, who had the best constant of around 65,000, 66,000. But still on the order D2 to the minus D. Although I should mention that Venkatesh manages to get a log D improvement on this in a sparse sequence of dimensions. But in terms of general bounds, this is the world record. Okay, what about upper bounds? The bound from the 70s due to Kapityansky and Levenstein, that it can't be sphere packings can't be any denser than 2 to the minus roughly 0.59 D. So there's this exponential gap in our knowledge here. I should mention there's been a constant factor improvement to this bound by Henry Cohn and Yufei Zhao recently, well, a few years ago. On the exponential order, this is the best known. So we have this giant gap, this giant exponential gap in our knowledge. Given such a basic question, it's sort of embarrassing for us mathematicians. It's like really a fundamental problem, and yet we can really say nothing about what these optimal sphere packing densities should look like. In particular, basic questions we have no idea how to answer is, are these high-dimensional packings, should they be structured, or could they potentially be highly disordered? So it's worth mentioning that the bounds of Venkatesh and previous bounds actually do come from lattice packings. So lattices are doing quite well, at least the world record is held by a lattice. But is there any reason to believe that lattices should be any good in high dimensions? Okay, so what I want to talk about today is a slightly alternative approach to this problem, which might give us access to potentially disordered packings in high dimensions. And to tell you about this, I need to introduce a basic model in physics called the hard sphere model. So the hard sphere model is one of the oldest models of a gas from statistical physics. It goes as follows. So just take a box. I've written bounded measurable space, but just take a nice box in RD. And what I'm going to do is I'm going to throw a Poisson point process down on the box. If I stopped there, this would be known as the ideal gas. But I'm going to condition on the event that these points are far away, separated by, say, 2. Another way of saying that is I'm going to condition on it being a sphere packing when I throw little balls around these points. So now this is a probability distribution on sphere packings, and this is known as the hard sphere model. So I started with a point process of intensity lambda. So when lambda is very small, that might look like something on the left-hand side. But as I crank lambda up, my intensity gets larger, I expect denser and denser packings. And you might expect to see some large-scale structure emerge as I crank up the density. This is what we might call a phase transition. But again, just to show you how far behind mathematicians are compared to physicists, it's a wide open problem to show that there exists a phase transition in this model for any dimension greater than 2. Prove that there exists a phase transition in this hard sphere model. It's wide open. Okay, but we can still study it. It's still a beautiful basic probabilistic model. This is also known as a Gibbs point process.
So you're talking about thermodynamical phase transition?
Thermodynamical phase transition, exactly. So you can define it in a number of different ways. In fact, what makes it so nice is you can think of it as, you can define it analytically as some non-analytic point and some partition function, or some free energy, or you can define it probabilistically. Do I have long-range correlations in this model? Does the position of a sphere here tell me anything about its the position of a sphere very far away. I could ask for a dynamical phase transition where I might have some dynamics, like lambda dynamics. Is there some slowdown in these dynamics of damping pieces? Any nice way you want to define the phase transition, some of these are equivalent. We have no idea how to prove the existence of such a thing. Okay. So what my co-authors and I did a few years ago was we studied the expected density. These are sphere packings. So we wanted to know what does the density of these guys look like, going back to the sphere packing problem. And what we found is actually quite surprising. We found that in expectation, this model is spitting out sphere packings on the order of d2 to the minus d. So on the same order as the densest known. So for lambda not too small, just an expectation, the hard sphere model is spitting out sphere packings of density 2 to the minus d. So of course, this shows that sphere packings exist at this density. The hard sphere model is just spitting them out. But they're quite different to the lattice packings of Venkatesh and so on, potentially highly disordered. And you can also get nice probabilistic information about these packings, such as lower bounds on their entropy. The entropy is just a sort of measure of how plentiful these packings are. In fact, you can just call it, the entropy is, if I take a packing at this density uniformly at random, or sorry, if I take a configuration of points at this density uniformly at random, what's the probability it forms a packing for the configurational entropy? So you can get nice statistical information on the space of packings as well from this approach. So I'll even attempt to sketch a proof of this fact, proof by picture. So what we can do is we do a two-part experiment. So I'm imagining I'm doing the hard sphere model in a box. I'm just sampling the gas in a large box. And first I'm going to pick a point uniformly at random in the box, call it V. Okay. Then I'm going to throw a little window around V of radius 2r. What is r? R is the radius of the sphere that I'm packing. You can think of r as 1 if you like. Okay. Now what I'm going to do is I'm going to reveal the hard sphere model outside of this window. So I'm going to reveal the hard sphere model outside. Maybe I get a smattering of points. And these points then come with some exclusion zones, don't they? Meaning if I have a sphere with center here, I can't have any other centers within a ball of radius 2r from this point. So the spheres would overlap. So these come with some exclusion zones. I guess the colors aren't really terribly convincing on the display, but these are sort of red exclusion zones anyway. And what this does is it sort of chomps out little bits from my window from the perspective of V. So I get a random set, a sort of random local view from V. And what's cool is I can now ask, what does the hard sphere model do in here? And it turns out it's just conditioned on seeing this. It's just the hard sphere model again. This is a general property of Gibbs measures. There's a nice self-similarity property of the hard sphere model that you can leverage. We have this sort of random set. Now I sample inside. And what you say is, well, if this random set is typically large, then I expect to see lots of things in this set in close to V. And that kind of gives me a lower bound on the density. On the other hand, if this random set is small, then I might not see anything in V's local neighborhood. But if I see nothing in V's local neighborhood, that means I could put an extra sphere there and augment the packing. So that kind of gives me another way of leveraging this viewpoint to give a lower bound. So in either case, there's a lot of hand waving going on here, but the takeaway is, in either case, whether this local view of V is small or large, I can get a lower bound on the packing density. And I can play these two lower bounds up against each other to give me a nice lower bound on the packing density of the hard sphere model. Okay. So this turns out to be quite a general approach, and it just really used the property of Gibbs measures. And so it's been useful in quite a few different contexts. Let me just explain discuss one more. This is a kissing number problem, another classical problem in discrete geometry. The kissing number problem asks the following. I have a central unit sphere colored black in this picture. How many spheres, non-overlapping spheres, can simultaneously touch the central sphere? Okay, this is in RD, say I'll call this the kissing number in dimension D. So the year is 1694. Let me actually just say, before I say the year is 1694, the year is still 2023. So I can rephrase this as a packing problem, right? Why is that? Imagine just radially projecting these outer spheres onto the middle sphere. What I get is a spherical cap. And now my condition is these spherical caps can't overlap. So all I'm doing is packing spherical caps on the surface of the sphere. And this is called a spherical code. Turns out the kissing number, you're packing caps of angular radius pi by 6. But you can ask for packing spheres of any angular radius you like. This is packing of spherical caps on the surface of the unit sphere. Okay, now the year is 1694. And Isaac Newton and David Gregory are in an intense debate over the value of K3. Isaac Newton thinks the answer is 12, and David Gregory thinks the answer is 13. So again, they're just wondering how many oranges can you squeeze around a central orange? So who do you think won this argument?
Given that this is a meeting of the Isaac Newton.
It's always a safe bet to go with Newton. But it took 250 years to actually settle this argument. And Van der Waal in the 1950s actually gave a proof of the fact that K3 is equal to 12. So Newton was victorious, so it took a little time for him to be vindicated. Again, I'm going to be interested in this in high dimensions, although I should say this is known exactly in, again, dimensions 1, 2, 8, 24, and 3, but also in dimension 4. So we know the kissing number in dimension 4, but we don't know the optimal sphere packing in dimension 4. This comes from the D4 lattice, which I think most people believe is also the densest sphere packing. Okay. You can give, again, this greedy lower bound, actually. Do you remember this doubling argument? You can just do the same thing here. Just pack caps greedily on the surface of the unit sphere until saturation, double the radius of the caps. It has to cover space. So that gives me a lower bound of the air. I just take the area of the unit sphere and divide by the area of the double cap. So again, greedy lower bound. And this is the lower bound you see here. It's actually not, it looks a bit confusing, but it's actually just this greedy lower bound that we've already seen.
Where's the little O1 come from?
I guess in approximations to the normalized area of a cap of radius pi by 6. So I've made some asymptotic approximation to the area.
That one didn't show up in the earlier greedy.
No, that was just 2 to the 9th. But that's because the volume of the double ball is
a more obvious.
just 2 to the d. Here it's some strange earlier cap. Yeah. Okay. And this was discovered independently by Shabowski, Shannon, and Weiner throughout the 50s and 60s. And this genuinely was the state of the art. The reason why this is a little bit trickier is lattices. It's really hard to find lattices with good kissing numbers. The lattices don't work, or at least we don't know how to make them work. But this physics approach works just fine. So what we did was run basically the same proof that I sketched. And the main point is that d to the 3/2 used to be a d to the 1/2. So I just want you to view this bound as a kind of Rogers type, and an analog of the Rogers type bound for the sphere packing problem, but now for the kissing number problem. And the proof is just a hard caps model. Just run the hard sphere model, run a gas on the surface of the unit sphere rather than in Euclidean space. And you can, the same type of proof, go through. I should mention there's been a recent improvement by a team in Warwick to this constant outcome here, using the same approach. Okay. Great. Any questions so far? I'm going to slightly change topic. How much time do I have, by the way? I can't remember what it is. 5 minutes. Oh, perfect. So we've seen that the hard sphere model had an illustrious history in statistical physics. is closely connected to this lovely sphere packing problem. Turns out it's also had a really distinguished role in the theory of algorithms. So I just want to pivot slightly. Here I'm going to become a little bit less formal and just talk more in generalities. But the basic question is, the hard sphere model comes along with very naturally with a computational problem, which is, can we sample from the hard sphere model efficiently? What might that mean? That might mean take a region of volume n. Can I produce a maybe approximate sample from the hard sphere model, let's say total variation distance at most epsilon, in time polynomial and n, and maybe 1 over epsilon the error. So can I approximately sample from the hard sphere model efficiently, polynomial time, let's say in the volume of the box? And let's say I'm packing the sphere for volume 1. And what is the connection between this computational problem and the physics of the system? What is the connection between computational complexity and phase transitions and so on? This is a sort of a beautiful area of, a still very active area of algorithmic research. And in fact, this was almost the very first algorithmic problem. So this is a paper from the 50s, which is the Metropolis algorithm came up in one of the talks, I think it was Greg's talk. This is the original paper, why it's called the Metropolis algorithm. You see Nicholas Metropolis, Rosenbluth, Teller, and Teller. The Metropolis algorithm was invented to sample from the hard sphere model in dimension 2. So they were doing hard disks on these early maniac computers in Los Alamos. So this gave rise to the Metropolis algorithm and in general the Monte Carlo Markov chain method. Here's a list of voted the top 10 most influential algorithms of the 20th century. So you probably might disagree with some of these, or it's probably a fairly controversial list. There you see the Metropolis algorithm there. I think it's
Who made this list? Is this your favorite?
So this is Rutgers. I think this is Rutgers University. It's slightly more authoritative than just myself. Yeah,
it's unordered though, right? This is just chronological.
It's just chronological. Yeah. I'm not.
That's a little safer. Yeah.
Exactly.
Or a transformer, you know.
And in general, just considering the problem of can we sample from the hard sphere model efficiently has given rise to a number of algorithmic techniques, not least the MCMC. But just the original problem of sampling from the hard sphere model itself, so here's this picture again, the only positive algorithmic results that we have is in this low density regime, where we're disordered. Here, Markov chains run well, or any method that might be based on correlation decay and things like that. We only have positive algorithmic results down here, and we have no idea how to sample in the dense regime. We don't even, if we had, say, a negative result in the dense regime, that would, of course, be spectacular, because that would be a dynamical phase transition.
It's over now, yeah.
The talk is essentially done. Actually, I wanted to show you a couple of simulations, if I have 1 minute. Just show you that there's some hope. So what do we do when we don't understand a problem in the continuum? We often discretize space. So what I'm going to do now is I'm going to do a lattice gas, and now I want you to imagine the squares as atoms, and I'm not going to allow neighboring squares to be occupied simultaneously. Okay. So this blue checkerboard is like a crystalline ground state, right? It's the densest configuration of atoms. Okay. And some red things are going to appear in a second. Those are going to be atoms on the odd sublattice. Let's say the blue ones on the even sublattice. And I'm going to run a Markov chain to sample from this. This is just going to be essentially the Metropolis algorithm, the Glauber dynamics of this model. And what you see is here, it's mixing quite quickly. In other words, it's very hard to tell where I started, right? This is what a rapidly mixing Markov chain looks like. This is what I want you to think of as the disordered regime. Okay. Let me just quickly crank up lambda. This is my intensity to say 100, or maybe let's try 10, slightly less dramatic. And what we see is a very different behavior. We're sort of stuck towards our initial crystalline configuration. This doesn't look like it's doing terribly well in terms of mixing of the Markov chain. But what you can do here, actually, is you can reverse your view and instead try and sample from this model by sampling the defects from the perfect crystalline ground state. You can sample defects. This viewpoint was, well, this technique was very well known to statistical physicists. It turns out you can actually make this algorithmic. And so that's a little bit of hope that there's no reason why phase transition could be a barrier to algorithms. The problem is in the continuum, it's very hard to define what you mean by a perturbation from a ground state. In high dimensions, we don't even know what the ground state looks like. But there's a lot of beautiful discrete lattice models where you can use these statistical physics ideas as well. Okay, so end there. Thank you.
So you might already know this and maybe part of the method, but one thing Henry Cohn loves is to use mean value theorems to kind of push up these bounds. So an expectation is there sort of enough information about the volume of configuration space that you could actually kind of bootstrap your mean value theorem to show that something lives much, that there's actually an existing packing at much higher density. Or
yeah,
not much higher density.
It's a really good question, and these best known low bounds do come via the Siegel mean value theorem. There you normally take some Haar measure on a lattice and kind of blur out the lattice. I don't know any way of using the mean value theorem in the absence of this kind of lattice structure. That's a really interesting idea.
I was asking you about if you know enough about the actual volume of actual configuration space. I mean, it's a hard question.
Yeah. That's a really good question. Something that I haven't thought too much about in this context. But can you use some low bound in the configurational entropy to say something to push you a little bit higher up in the density?
Yeah, this was that little comment, the bottom.
Yeah, actually, I have thought quite a lot about this in a related context, and I have never made it work. But yeah, it's a really natural, beautiful idea. Yeah.
Okay, let's think that figure again.